Everybody, we're here at the center stage with the red highlights, and we are very happy that you're here. And this is a very selective topic, so there are not many people, but we ask for a large room so that you have enough space that you can sit back, relax, and can enjoy a new and cool topic with us. I hope you're comfortable yet. And so this topic is about LLMs, like so many topics are today, but we have a twist. There's a new side to LLMs that you may not have seen before. But let me calibrate with you quickly. Who of you would be able to explain to the rest of us what an LLM is, but more importantly, how do we use self-supervised learning to learn about the world around us? I'm not going to ask you to, but would you be able to explain this to the others? Okay, a few are, very good. But even if you know everything about LLMs already, there will be new aspects that we want to talk about. But in particular, we're going to apply them to structured data, which to this day is still at the heart of all enterprises. And we're going to apply this to anomaly detection. And for anomaly detection, who of you knows what it is and how this works? All right, roughly the same people, it seems. And for the rest of us, it's what it says on the tin, that we are looking for the needle in the haystack. And I hope you can appreciate that this is a hard job, that you have this one small needle, but you have all this many hay that we want to compare this to. But in our case, it's even harder than that, because we do not know how many needles are there. Maybe is there a needle? And most importantly, what does a needle look like? But fear not, we have a solution, and we brought the slides to prove it to you. And if you don't believe in slides, you also have an extensive demo. Which leaves us with the most important question. Why would you care? What's in it for you? And we know what many of you do for a living, so it's clear that you may not be that interested in hay. You may not even have a barn for all this hay. But luckily, we have Ahmed with us, who is not only a world-renowned solutions architect, but also a bridge builder. Ahmed, do you want to bridge this gap for us?
Of course. Thank you, Mariano. And hello, everybody. I'm super happy to be here with you. Let me introduce myself. I'm Ahmed, a solutions architect. But for today, I'll be the bridge builder connecting Mariano's story to real-life use cases. We have a very exciting things to show you, so let's just get right into it. And let me start by talking about the applications of anomaly detection. And let's take a few use cases. We start by talking about fraud. And most commonly, credit card fraud. Quality assurance. So making sure that maybe if you're manufacturing a shirt, that it is up to the standards of quality. Finally, inspection. And let's think of a network traffic or logs. Just looking through any of these two and alerting you if anything looks too weird. But the question is, why are we coming up with a different approach today? Let us look at the challenges with the current approaches. First one is the size of the data. Now think of any modern system. It has maybe millions of rows of data. And traditional anomaly detection systems, they struggle with this amount of data. Data comes in all forms and shapes. So the second challenge is the format of the data. Let's think of a row of data. That might have very complex relations between the attributes. And that is a challenge for traditional anomaly detection systems. They struggle dealing with the complex relationships of the data. Finally, patterns. Going back to the credit card fraud. You need to see a pattern before you're able to detect it. So for example, if somebody is using a stolen credit card, they might go to a gas station, maybe try to figure out if the credit card is still working, or if it was reported as stolen. If it's working, they might take that credit card and go to a bigger retailer, and then buy a more expensive item. So that's a pattern that we see, that they first go to a gas station and then to a bigger retailer. But what if these fraudsters come up with a new way, and we don't know the new pattern? Then we will not be able to detect it, and then it will go through as a legitimate transaction. So instead of doing it this way, what if we can go the other way around? So instead of figuring out a pattern, we try to figure out what everybody does in their daily life. And we consider that the normal. And if something deviates too much from the normal, then we flag it as anomalous. And we take a look into that. For today, we're going to be using the New York City cab ride dataset just to show you what we mean. But let me go back to Mariano's story. So you don't, or how can you figure out what is normal? How does a hay look like and how does a needle look like? For us humans, that's very easy. But for a model, how does it figure out that this looks like hay and this is a needle and they are two different from each other? Mariano, do you want to show us how?
Absolutely, I'm glad you asked. So we have tons of data, like millions of these trips in New York City. But how do we learn something from it? How do we detect those patterns? And the concept we are looking at is sequences. So sequences like in here, we have those 4 elements that form a sequence in order. And it could be something like, for example, coin tosses. We start with a head, then a tail, and a tail. Now, what we want to do is see, can we see patterns or something that we could make a better prediction about what is the next element in this sequence? So is the next element maybe something like a head or a tail, or we don't have enough information to say? So let's do this as a poll. Do you think the next element we see is heads? Do you think it would be tail? Or do you think we don't know? All right. As most of you saw, already predicted, we don't have enough data. And the reason for this is that there is no cosmic balance that we need to get back to or something. The coin doesn't know about being balanced. The coin doesn't have a small memory. The whole data generation process is completely unbiased because all of the coin tosses are independent of each other. And because of that, it doesn't really matter if we were to look at 1 million coin tosses, there's really nothing for us to learn from. But we have more sequences. Let's look at the weather. We start on Monday with rainy weather, and then we have sunny weather, sunny weather. Now the question then is, what is going to be on Thursday? And I want to query you again. Do you think it will be raining on Thursday? Or will the sun be shining? Or we just don't know? Okay, I think this was kind of a split. So the answer is, if you want to have the most likely event, it would be the sun, and that we would see the sun shining. But the reason for that is that we have a dependency now between the days, between the different elements in this sequence. And based on this idea, this is easy to understand, but not so easy to see just from the example, but it gets a little bit easier if you say it's not from day to day, but it's from hour to hour, or maybe even from minute to minute. And now, if you look at this from minute to minute, this should make sense for your general understanding of how the world works. There is a physical process that is generating our data. And we now, if you look at the sky now, and it would be showing us rain, there would be also clouds. And if you want a minute later that we have the sun shining, there's a blue sky, those clouds need to move away. So there's something physically happening. So the data generation process would also reflect this. So if we were to look at like 1 million of these events, we would be able to learn something meaningful from that. And you have seen this in action when you talk to a chatbot, because that's what an LLM does as well. We have these tokens, and they say, for example, bird in the, and now we go through the same steps. We have these choices, and here in this case, it's a vocabulary in our LLM. And so we have all of these different tokens, all of these different words. But I'm not asking you now, I'm asking the model, what will be the scores? What would the model raise their hands? And we can see that if we say bird in the hand or bird in the cage, this is very likely plausible. We have a high score. But even bird in the bed is possible. But to know which of those are plausible, we actually have to run the numbers first. And we have to compute for every of these tokens, let it be like 100,000 in vocabulary, this computation of the score. Because before that, we don't know what is plausible, what is likely. And so this includes Uzbekistan and every other token what we need to have a number for. And we can learn from all of this because once more we have dependent events. And so this, for example, means that if we say tree is our next word, then we would not only say it's depending on the, but it's depending on bird as well and in. You know, if I would change the word bird to dog, it could still be bird in the tree, it could still be dog in the tree, but much less likely with dogs. But for example, dog in the bed would mean it goes up. So I learn all these dependencies from every token that I have before, and then I learn what is the next best prediction that I can do. Now, the question, of course, is where does a model learn all of this? And it's a neural network. But there's one part of the model that is cordoned off where we have a specific part for each of the tokens that it's seeing during training. These what we call embeddings. And you see there's a few small numbers. This is basically where the neural network and the training process takes note to have some numbers that make it more powerful when predicting the next word. Now, one of the things that made it easy for you to follow along with the story is that you already know what a BIRD, what a bird is, because you have been walking this earth for like, I would say at least 20 years when you're in this room. But just imagine there's a newborn, or like a newborn model that is just at the beginning of the training. It knows absolutely nothing about what these BIRD letters mean. So it needs to learn something. And this means to us, we look at this like symbols, because the word itself doesn't mean something. It's like I would ask you, with this sequence, you can clearly see that there are colors and that there are shapes, but what would be the next one in here? If I were to ask you, with the same steps, we have this dictionary full of choices, which one would you choose? You wouldn't know. But what if I gave you like 1 million of those sequences and a little bit of time to look through them? You may find that there are some patterns that would make you better in doing these predictions. And this is how the LLMs work. And you can hopefully see here that it's a much more general process that not only works for words and tokens, but in language, it would also work for anything that can be tokenized, and almost anything can be tokenized. So if you would be creating a self-driving car and there are a few camera feeds from around you that create image data, you can tokenize it like you can do for sensor data from the pedals or from the steering wheel. And so you could learn from all of this data to predict the next move that, for example, the pedal should be doing. But we're not going quite that far, even though it's something about cars, but we are looking for the New York City cab rides. And now, to make this more specific, Ahmed will tell us what are the next steps.
All right, let us talk about the next steps we have taken. So as a first step, we started by preparing the data. And again, to talk about the data, we are using the New York City cab ride dataset. Most of you already know this dataset, but for those who do not know, it's a public dataset. It talks about taxi rides happening in New York City. We have taken 20 million records. We have mapped these as JSON, and these are trips from 2018 to 2023. Now, after talking about the data, let us walk through how we have mapped the data. And we start by a middle block here, preparing the data. And before we're able to work on the data, we need to download the data. So we download it from the internet first. We do some processing over the data, and finally, we have the JSON data. Let's take a look into more details about the data preparation. So now, on the left side, you see this is how we downloaded the data. Let's look at the first row in the table here, and we have mapped it to a JSON, just as you see on the right side. Let's focus on the fare amount here and ask ourselves, how do we map this into a sequence of tokens? We do this by dividing it into 3 different tokens. So you have the fare token, 2.18, which is a value, and the fare is a key, of course, and then the comma, which represents a structure of a JSON. And doing the same steps Mariano have did before, what comes next after this? We can look at the choices. And I would like to ask you, do you think comma could be the next token here? Yes? No? We don't know? So as most of you have said no, you're correct, because you probably have dealt with thousands of JSON data throughout your professional career, and you have never seen a comma next to another comma in a JSON. But let's check with the model. What does the model think? And of course, the model tells us, yeah, it cannot be a comma, and the most likely token is the distance. And why is it the distance? Because throughout all of the training data, the model has seen fair token, a value, comma, and then the token distance. So the layout of the data, or the ordering of the attributes, were always like this. Now let's consider that the data preparation has been done. We go to the next step, which is the training. And we start by preparing the tokenizer. So we're using a custom tokenizer here. And to prepare that tokenizer, we need to read in the data. And then we do the training of the tokenizer. Then we get a custom tokenizer. Afterwards, we work on the model. So we prepare the model. And to prepare the model, we need the data and also the tokenizer. And that's exactly what happens here. So we feed it in. And then we get an output, which is the model itself, or the model artifacts. We save that on S3. And we get some metadata related to the model. And this is saved on SageMaker, or Amazon SageMaker. To make this whole process easier for us, we are using SageMaker pipelines. And for those of you who do not know what SageMaker pipelines are, it's an orchestration tool. And going a bit more, in SageMaker pipelines, we just define 3 steps here. So preparing the data, preparing the tokenizer, and preparing the model. SageMaker pipelines take care of the input and the output of each step. And basically, SageMaker pipeline saves it on S3, the output of each step here. We have a processing job for preparing the data and a SageMaker training job for both the tokenizer and the model. And with a click of a button, we are able to rerun the whole pipeline. And why is this useful? Because we want to try different configurations of the data set. We want to try different configurations of the tokenizer and the model. So with a click of a button, we are able to just get the trained model in the end. And this is how it looks like on the UI of SageMaker pipelines. And you can see these are the 4 steps we have done previously. Now that the model has been trained, we go to the last step. And this is the inference. This is where we're going to ask the model, take this row of data and tell me if any of the tokens here look too weird to you. And in that case, it's anomalous. This is exactly what we're going to see in the demo now. And Philip, please take us to the demo. All right. So there's a lot of things happening on the screen here, so please follow what I tell you and follow the cursor on the screen. If we look in the middle part here, you see this is a row of data. This represents one cab ride happening in New York City. This is the first time you have seen this row of data. Similarly, that's the first time the model has seen this data as well. So this is taken from the test set. What you want to do with the demo here is look at individual tokens. And for every token, we ask the model, give us the predictions. And we look at the predictions and compare them to the token shown on the screen here. And to give you more clarity, let's look at the first token here, the opening curly bracket. Now you see there is a table shown below. It has the top 10 predictions done by the model. One of them is always highlighted in orange, and this is the same one that is in the data itself. In this case, the most likely token is the opening curly bracket, which is exactly the one in the data. And the model is highly confident that this is the right token. Let's look at the comma here. Similarly, the model is very confident that it has to be a comma. Let's look at the closing curly bracket. Similarly, the same thing. And what can we deduce from that? So the model was able to figure out how a JSON structure looks like. It has to start with an opening curly bracket. There are some commas in between the attributes, and in the end, a closing curly bracket. Now let's make it a bit more interesting and look at the pickup year. But we see the same thing again. Pickup month, same thing. Pickup day, same thing. Because in the ordering of the data, that was always the case. It starts with the opening curly bracket, then the pickup year, value, comma, pickup month. And then it goes to the end, and then there's the closing curly bracket. Let's make it a bit more interesting and look at the values. So let's look at the token 23 here. Now we see a few different predictions by the model, and we see tokens from 18 to 23. And maybe it clicks in your head. The training data was trips happening from 2018 to 2023, and that's exactly what we see in the table below. Now let's look at the pickup day of the week. This is a 5, and this is a value. Now the model tells us it's highly confident that it has to be a 5. Why do you think that's the case? And I would give you a little hint here. So this 5 is conditioned on everything previous to it. And maybe you have realized we have the pickup day, pickup month, and pickup year. So this is the 8th of December, 2023. If we look at a calendar year, it's a Friday, and that is the 5th day of the week. So the model was able to figure out how a calendar looks like, basically. Interesting, isn't it? But it doesn't just stop here. As mentioned before, this is taken from the test set, so we do not expect any anomalies in this row of data. So what we want to do is we want to introduce a change here. And instead of starting the trip at 15, we're going to start it at 1 hour previous, so at 14. And give me a second. Okay, give me just a second. Let me fix this.
How did you like the UI so far? It's actually something where we put quite a lot of attention into it. Because when I say we, I mean, there's a lot of effort and it paid off very well. Because if you compare this and contrast this, how you do traditional software development, you basically have an idea, you start implementing it, and it works. It's probably not as much as a straight line as I make it out to be. It's more of a squiggly line. There may be a lot more tears and a little bit more sweat. But at the same time, this works very well, usually. This is not at all the case for data science. We have an idea, maybe a crazy idea. We have some data, and then we very, very slowly approach the idea to implement it in many, many different steps. So we cannot really tell the model what to do. But we have to listen very carefully what it does. And let me just finish this quickly. We have to listen very carefully what it tells us. And so this is kind of more like that you're the model whisperer. And that you can encourage the model to learn something or discourage it, but it's not that you can tell it what to do. And the screen that you're seeing here right now, this has like 50,000 numbers. But it's now contextualized so that you can interrogate it and understand what your hypothesis is working out, because you would never be able to go through this with 50,000 numbers. Back to the demo.
All right, so we're back in action. Sorry for that. Let's look at the drop-off hour again. So now we see the model tells us the most likely token is 15. And how do we interpret this? So the pickup hour is 15. We know we're going from East Harlem North to Central Harlem. And the model tells us this trip doesn't take that much time. It takes around 8 minutes. And we can see that this from the pickup minute and the drop-off minute here. So the model tells us the most likely token is 15. Now, the change we want to introduce here is instead of starting the trip at 3 p.m., we're going to start it at 2 p.m. And now you see in the close to my cursor, we're updating the value from 15 to 14. Now let's look again at the drop-off hour. Now we see a massive change. Previously, the most likely token was 15. Now it's 14. And the 15 is not likely anymore. This makes us calculate an anomaly score of 1.00. In this case, it's the probability of the most likely token, which is the 14, minus the probability of the token 15, which is shown on the screen here. So the model was able to figure out, just by updating one value, that something looks weird now. But so far, we have looked at individual tokens. What if we do this for all of the tokens shown on the screen here? And this is exactly what we do now. You see, the 15 is highlighted, or has a border underneath it in red. The brighter the red, the more anomalous it is. And we can see some other tokens are anomalous as well. We can take it one step further. Now, we have introduced this change by ourselves. So we don't know if the row of data came like that. How can we figure out what is wrong in this row of data? Or what made the model decide that this is wrong or anomalous in this case? We can turn this on. And now you can see some highlighting going on the screen. And most fascinating, the 14 being the most yellowish token on the screen. And we know this because we're the ones that changed the 15 to 14. So we know this introduced the anomaly. But the model tells us now that 14 is the most influencing token into making the decision that this is anomalous. Fascinating, isn't it? Mariano, how did the model figure this out?
Thanks for the question. So all in all, we have like 25 minutes of demo in here, and who could have thought that something would go wrong? Huh? But before I go into more details here, so this is about that we explain an anomaly. And why is it important? Because an anomaly is not a finding. This is more a candidate of a finding. If you go back to the original story about this purchase in the gas station, we want to help this payment process, and we may return a high number, a high score. And so there may be some automatic program that would say if the score is above 0.9, we categorically deny this transaction. But we could also say if it's above 0.5, then we would introduce additional friction to this process, like to ask the purchaser for additional ID. And this becomes much, much more powerful if you don't only have a score, but we could say, what is the influence of the score? Why is the score that high? This is helpful for an automatic program, but of course also if I were to give this to a human being to do a second level check. And this is what we do to turn these candidates into actual findings, and we're trying to support this. So in this UI, you already saw that 15 here, this is a number that we currently have in focus, and we asked the model, what would the model have done in this place? And we saw that given everything else that comes before this, that we now have 15 as one possible solution, but it's very unlikely, while 14 is something that looks much, much more likely, because we have seen during training that if a trip starts at 1400 and we start in East Harlem North and we go to Central Harlem, which is a short trip, then we would expect the number not to be 15, but 14. And the difference between the most likely token and the chosen token, this is what we call our anomaly score. So if you think about it, how would you get this anomaly score to 0? Think about it for a second. If we had the same token, that's the most likely token, so what the model says, this is right, and it's also the token from our observation, then the anomaly score would be 0, which should make intuitive sense. But how do we get to the explanation? I want to give you a technical description first, and then I will explain this in more plain English. So we have this anomaly score where we say this is this difference that we are computing, this is differentiable, and so we could say that we compute the partial derivatives of the anomaly score with respect to all of the tokens all of the positions before it, and each of these positions carries these tokens, and they have an embedding, and the embeddings, they have dimensions. Those little numbers I showed you before. And based on this, we can compute the influences. And I know this was a mouthful, but the important bit is if you understood these terminologies before you came here, you can see there's no magic involved. That's just something that you can do relatively easily. But in plain English, it means we're looking at this 15, and we know that it's influenced in the prediction by all of these tokens above here. And we know that we have this anomaly score 1. And now we understand that each token can have an influence, but how much? So we go through each of these tokens, let's say to pick up months, and we make it a little bit smaller or a little bit bigger. So we say we perturbate it, and then we recompute the anomaly score. If it goes up or down, this gives us an indication of in which direction is this token changing the anomaly score, and it tells us how much. And we call this the influence. And we do this for all of these tokens, and then we take the top 10. These are marked here in green. These have the strongest influence, and we put them into this table. And so we can see that 14, that's our strongest influence, and it has some number that doesn't make much sense to us, but we say because it's the strongest, we make it 1. And then we have the weakest, which is Manhattan, or the weakest of the 10, and we make it 0. And everything in between, we're resizing appropriately. So we can have a good understanding of how important is this value for the anomaly score to go up or down. And I hope you can see if you're the human who has to look at this and understand why this is an anomaly, or even if you're a program and you should have a more sophisticated set of rules as I described before, this can come in quite handy. I will come back to this, but I want to show you another feature. And if you think about that you want to deploy this into production to New York City, and then something happens, for example, that the Holland Tunnel is flooded, or that there's a new construction site that you have never seen before, what do you think it will make to the accuracy or the quality of your prediction? Are they going to go up or down? I'm not going to poll you, it should be obvious, correct? They go down. Of course, they get worse because something happened in the real world that the model has never seen. The model was trained to some point, and then we stopped learning. But the world kept turning. And so we say that the model drifted. And so for model drift, we have a solution. So first of all, we have a name for this. It's model drift. And we have a solution. It's to retrain the model. But if you want to be sensitive to something that happens like 5 minutes ago, then you have to retrain it a lot of times per day, which would be uneconomical. But we have a better solution to this, and we get the solution for free. Because what you're looking at is an LLM. It's a large language model, even though it's not large. It's just a few million parameters. Even though we're not using natural language, but we're just looking at structured data. But it's the same code, the exact same code, like for any LLM, like for any training. So we're walking on the shoulders of, or we're standing on the shoulders of giants, and we get a lot of features for free. One of them is prompting. You remember prompting, if you go to an LLM, you have your question that you ask to it, or you describe your task, and then the LLM is generating an answer, and each of the tokens is conditioned on this prompt. And so the information that you give into this prompt will influence the generation. So this is something that we call in-context learning with an LLM. And this is what we're going to use as a solution. Below here, that is the same record we were looking at the whole time. By the way, where's our time? Okay. This is the whole record that we were looking at the whole time. This is what Ahmed was showing us before. But now you see that there's a new record above this. This is the trip actually from the test data set directly from the one that we're now looking at. And during training, the model has seen many, many trips, like 20 million of those trips. And oftentimes we had like, for example, let's say 5 in a context window. The important thing is they were always chronologically ordered. So the model learned that if there's a trip later in the context window, it will also be later in time. And what I'm getting to is that if we now predict how good is this, what would be the right starting point for a new record, it is still an opening curly brace. And we would still start with the pickup year, exactly as before. But do you remember the values for the pickup year that Ahmed was showing us? It was 2018 to 2023. This is no longer the case. We have learned in context that we have only 2023 now, because what we showed the model during training is always that they were chronologically ordered and relatively close together. And we can even ask the model to explain this in a little bit more detail, and we go back to this idea of computing partial derivatives, this time not of the anomaly score, but of the prediction itself, which we will call the logit. And if you look at this, you will actually see it's not about anomaly score. It's just about what was important for the model to make the decision to put 23 in here. And it looked at the label, of course, that's the positioning. But then it says the most important thing, actually even more important than the label, is the value of 23 in the drop-off here. It also looks at the pickup here and other things, but clearly we can see that the model understood that it needs to decide based on what we gave it, which could carry newer information here as well. But we were looking at anomaly scores, and so let's go back to the idea from before. We have this pickup hour 15, and you saw what Ahmed did, that we do an intervention, that we changed this value to see what the model would tell us. And here, this time it's different. Before, the pickup hour was not marked as anomalous, and the reason for that was that it was only conditioned on the trip starting on the 8th of December. And if you start at 2 o'clock, 3 o'clock, 4 o'clock, it kind of is the same thing from a probability perspective. But if you now say that each of the tokens, including this 14, for example, here, is conditioned on everything, then it happens that it knows it has to work in the context of a 2023 trip that just happened before. And so this time we see this is marked here as well. And we can see that the model tells us there's a conflict with the pickup hour of the trip before, because as I mentioned, chronologically ordered. So what we're doing here is that we're traveling back in time. And the model has never seen that during training, so it says, look at this is weird. And we also can show that it now says the drop-off hour is wrong, as we did before, and it shows the most conflict is with the 14, but we can also see it takes into account the wider context here as well. I hope you can see how this is an LLM working with the same methods that we always know, but we can apply this to structured data and get some new insights from it that weren't that obvious otherwise. And with that, I would hand it back to Ahmed to take us home.
Philip, please take us back to the PowerPoint. All right. So talking about our next steps. If you found anything exciting today, or you have a use case that maybe brings you, as soon as you see this, you want to try this on, we are aiming to publish this as an AWS sample, hopefully in the next 6 to 12 months. So stay tuned. You know where anomaly detection runs best? The European Sovereign Cloud. All right, this brings me to the last slide here. I would like to thank you for your time. I know this is the last breakout session of the day. I would like to ask for you to just fill the survey so that the AWS gods can allow us to be here next year. And we're going to be off stage, maybe here, taking just a few questions. And I know it's the networking reception time. We're also going to be there. If you want to just reach out to us, just come in. Ask us any question. Doesn't have to be generative AI related. And we also have our LinkedIn if you want to connect with us. Again, I thank you for your time, and I hope you had fun with our session. And please do fill the survey.